In this video, we'll be investigating the Biot-Savart law for a long straight wire. Now, this is a problem that we went over in the last recitations before the break, but that's been a long time, and we're transitioning to a new format for the recitations, so I thought it might be instructive to actually review this problem again and just remind ourselves where we were before the break started. So we're considering two long straight wires, both carrying an identical current I going in the same direction. And by long wires, I merely mean that we're going to ignore any effects due to the ends of the wires on the magnetic fields. They do have a length L. So we have two wires of length L separated by a distance R, both carrying currents I. Now, as we've learned, not only do magnetic fields exert forces on current-carrying wires, but currents can also create magnetic fields. So, for example, any wire carrying some current I has a magnetic field given by the integral form of the Biot-Savart law. Now, you may recall earlier in the course that we had an analogous law, Gauss's law, for finding electric fields, wherein we had the field, in that case the electric field, given in terms of the integral of some vector expression on this side. But we didn't actually evaluate that integral each time. We did it for a couple of shapes, like for example the sphere or the cylindrical shape, and then used the expressions derived from those integrals to actually solve problems. And we're going to do something analogous this time. So the magnitude of the magnetic field generated by a long straight current carrying wire by the Biot-Savart law turns out to be mu naught upon 2 pi r. Mu naught, by the way, is just a constant. It's called the permeability of free space, and it's analogous to epsilon naught that we dealt with in electrostatics, only for magnetism. And that's just something that you can read out of your textbook. I, of course, is the current, and then r is the distance away of the point where we're finding the B field. Now, what about the direction of the magnetic field? So, this is a cross product right here. It so turns out that the direction of the magnetic field is given by a form of the right-hand rule wherein we point our thumb in the direction of the current, and the magnetic field is circular and points in the direction of your fingers at every point. So you point your thumb in the direction of the current, and your fingers give you the direction of the B field. Now, I've given no justification whatsoever for how we got from here to here, the general Biot-Savart law to the Biot-Savart law for the current-carrying wire that's straight. This derivation is in your book in section 29.1, so if you're curious, you can find out where this expression actually came from. But for now, we're just going to use it to solve the problem. Now let's turn our attention back to the problem. So we have two current-carrying wires, both with equal currents I, they're R apart, and of length L. And we wonder what is the force between these two. So that's the question that we're actually trying to answer, is what is the force between these two? Now for each of these, which I'm going to label 1 and 2, there's a magnetic field created by wire 1 that's going to be felt by wire 2, and because wire 2 is carrying the current, wire 2 is going to feel a force as a result of that magnetic field. And of course the reverse is also true, that current 2 is creating a magnetic field that exerts a force on current 1. The first thing I want to do is to think about this problem conceptually and try to determine whether this force is going to be attractive or repulsive. So pause the video right now and try to think through this problem just based on the way the currents are going and see if you can answer this question. Is the force pulling the wires together or pushing them apart? So now that you've had a chance to think that through, let's go ahead and solve the problem. So we know that wire number 1 is creating a magnetic field that swirls around in this direction as determined by this form of the right-hand rule, like this. Because the current is going upward, the magnetic field twists around in this direction. And the same is true for wire number 2, which I'm going to draw in a slightly different fashion. But go ahead and do the right-hand rule and convince yourself that these two are indeed going around in the same directions. Now we only need 2 bits of information to solve the problem. The first we've already worked out, and that is the magnetic field due to the current carrying wire. And the other one is, what is the force felt by the other wire due to the magnetic field from the first. And you may recall that that is given by IL cross B. The magnitude of that force is then ILB sine theta. Theta being the angle between the two vectors L and B. Now if we can imagine, instead of looking at the wires straight on, we're going to look down at them, like this. So this is wire 1, and this is wire 2. We'll notice that the magnetic field at the location of wire 2 from 1 is pointing straight upward like this. Or, in relation to the first picture that we had, it points straight back into the board. That means that the angle between L and B is 90 degrees, so the sine of theta becomes 1. And quite obviously, by the symmetry of the problem, the same thing is true for the B field from wire 2 at the location of wire 1. So the expression for force simply becomes ILB. Now, to find the direction of F, recall that we point our first finger in the direction of L, which is this way, our middle finger in the direction of B, which goes back into the page, kind of like that, and that means that F points in the direction of your thumb, which is to the left. And that's for the force on wire 2 due to the magnetic field from wire 1. Now this is a little bit more difficult to see without actually doing the right-hand rule with your hand, but if you work it out, you will see that F does in fact point to the left. And if you work out the direction of the force on wire 1 from the magnetic field produced by wire 2, you'll see that I points in the same direction, but this time B points out of the page like that, and that F points to the right. And clearly this is an attractive force. Now the last thing to do is to substitute this expression for B into our expression for force. So we get IL, this is our expression for B, so mu naught, another I, and then over 2 pi r. Now, of course, we can write this as I squared L mu naught over 2 pi r. And this is where to be careful, because this is only I squared because these two currents come out to be the same. And if you see a problem similar to this in the future, where instead these currents are maybe I1 and I2, where I1 and I2 are not the same, then this expression no longer holds, and you'll have to have I1 and I2 in here separately. But at least for the way I've written the problem, where I1 and I2 are the same, where we just have one current I, then we can write it this way. Now, for the actual problem we've been given, we're told that the wires are 6 centimeters apart, that the current is 3 amps, and we're curious to know what the force per unit length is. The force per unit length is simply F upon L, which we find by dividing both sides of this equation by L. That's I squared mu naught over 2 pi r. Mu naught is simply 4 pi times 10 to the minus 7th Tesla meters per amp. Now, since we are calculating force per unit length, the units are going to be newtons per meter. And if we use a calculator, we see that the answer is 3 times 10 to the negative 5th newtons per meter.